Hi, Spring fans. Welcome to another installment of Spring Tips. I want to help you make your application even more efficient and even more performant. But it's important to remember, Java is already an amazing ecosystem and an amazing technology, and it is very fast and it is very efficient. I think this is well borne out by this blog, which covers a study that was released in 2018, and it asks a very simple question: which programming languages use the least electricity? And if you look at this table, you see some very interesting results here. C is the most energy efficient for machines. Very important stipulation there. Not for people. Definitely not for people. Rust 1.03, zero cost abstractions. Very nice. Well done. C++. Tooey, disgusting. Moving on. Who cares? And then Java, right? And Java is 2.0. Let's round up. Let's just say it's the worst of the worst. 2.0, so it's twice as inefficient as C. That said, still top 5. Very, very efficient language, right? And then these other numbers are kind of interesting as well. The one that I like the most is, of course, JRuby. JRuby here is Ruby implemented in Java, and it is 46.54. Here's Ruby, which is Ruby implemented in C, and yet it is almost 70. So, you can see that JRuby, by dint of having been built on the JDK, is actually quite a bit more energy efficient. And remember, it came later. It's not like it had the first mover advantage or something like that. It just has this really amazing platform. So Java is already very energy efficient, and it's also very fast. You might have seen the 1 billion row challenge. My friend Gunnar Morling laid out this challenge earlier this year and at the end of 2023, asking people to parse 1 billion rows of weather station telemetry data, which amounts to about 13 gigabytes of text. And there's hundreds, if not thousands, of submissions that were submitted. The rules are very simple. You can't use a framework. There's nothing on the class path. It's just Java and a compiler. Now, it doesn't have to be the OpenJDK compiler, but it has to be, Java source code in binary of some sort out. And so the first 3 submissions, all of them are pretty impressive, but the first 3 just tell an amazing story. 1.5 seconds to parse 13 gigs of data, to load the JVM, to load all the types, to analyze the text, and then print out the statistics after having done the analysis, and then exit the program. 1.5 seconds to do all of that. Now, and that's, admittedly, that's using GraalVM native images, but the fourth one doesn't, and it's at 1.88, so 1.9, so 0.4 seconds, a little bit slower than this, but still very, very credible, right? Nobody would complain about that at any kind of scale, right? That's an amazing result. So Java is already both very energy efficient and very fast. What we want to do is just make it that much faster and that much more efficient and that much more scalable. So today we're going to talk about a number of things you can do to your Spring Boot application. Some of which are brand new, right? Some of which enjoy brand new support in Spring Boot 3.3, namely the CDS, class data sharing support that just landed. And this, of course, dovetails very nicely with a recent announcement that the Project Laden early access builds are now available. So let's dive right into it, as always, by going to my second favorite place on the internet. We're going to call this service. We're going to bring in the GraalVM native image support. We'll bring in the web support. We'll bring in the Postgres database support. We'll bring in the Spring Data JDBC support. And can I add CRaC on here? No? Okay, we'll just leave that as is. All right, so we've got a number of different dependencies here. I think we want a database, so I'm going to add I've got that already. You might want to bring in Docker Compose to get a Docker file that'll start up your Postgres database. I've already got a database to which I'll connect to keep things simple, so we'll just ignore that. Hit generate, and then open this up in your IDE. Now bear in mind, I am using SDKman, which is SDK Manager, right? SDKman.io, and I'm using SDKman, and I can look at the versions of Java that are available to install, and you can install any of a number of different ones. I'm using the GraalVM Community Edition, which, for all intents and purposes, is GraalVM OpenJDK, which is, it's just a distribution of OpenJDK plus some extra dependencies. I'm using 21.0.2 GraalCE. So SDK install Java, and then that. And then you can make that your default across all shells. SDK default Java, and then that. In my case, it's already done, so I don't have to do anything else. But bear in mind, that's what I'm using. For most of our demos, we'll just be using OpenJDK or something similar, like Azul. But you might also want the GraalVM compilation support, and we'll look at that as well today. Now, I think we're ready to begin actually writing some code. So let's build a simple example that does some simple things. first and foremost, I mentioned we have a SQL database. So we're going to create a password and a username. So my user and the password is secret. Don't tell anybody. Okay. And we'll have the URL, JDBC, PostgreSQL. And I'm going to create a new password here just so I don't have to override that. Okay. So my database. Okay. And then we'll take this and host name will be localhost by default. Okay. And then finally, I want to tell Spring Data JDBC what the dialect is. That can avoid some speculative sort of analysis that has to get done without requiring me to do a connection to the database. Okay. All right. I'm happy with that. I think, this is also in order to make this application more scalable. If you have access to Java 21 or later, and of course Java 22 is GA at the moment, but I'm using Java 21, then enable virtual threads. You have no reason not to, especially for a brand new application on Java 21. And then I'm going to make sure that we also never initialize the database. Okay. There we go. So I've got my basic application. Virtual threads are huge. This will help you with your RAM consumption because it'll allow you to sidestep creating so many threads. So this is actually very good for RAM. It also just means you can handle more requests with the same JVM. I've done a whole video on this. I'm not going to rehash all that now, but suffice it to say, super, super good idea. We also want to customize our build. This is another thing you can do for all workloads. It doesn't matter it doesn't matter what JDK, it doesn't matter what, your particular use case is. This helps for everybody. You can have Spring Boot do some, transpilation of your code and then have that loaded instead of the code that you feed it, right? So basically we'll transpile the code to make it more efficient and just use that. And you can use that on the JRE. Typically this gets invoked in the compilation during GraalVM, but again, you can just use that in a regular application. Okay, so what do we want to do in our application? Well, let's imagine a few examples here, right? And we want to take note of the startup time. That's very important. It doesn't matter if it's exactly the same as long as it's consistent. And so one way to do this might be to have a few variables. Okay, I'm going to have a few atomic references containing instance. Okay, start, and I guess we want to make this static actually, equals new atomic reference. There you go. And stop, and we'll get rid of that. Okay, and now we want to make sure that we want to make sure that we set the start as early on as possible. So that one's fine. Okay, and then we want to set the stop as late as possible. So I'll just create a component here, static class stop, startup listener, I guess, implements. Actually, we can just do this, event listener, application ready event, dot class, void, ready, and we'll say stop dot set is now, okay? And make this a Spring Bean. Very good. So there's our component. It'll update that variable when it's done, and we'll have that available to us. Now I want to make that information available in an HTTP controller. So let's go down here. We'll say at controller, at response body, and we'll say class, endpoints, whatever, who cares? We just want to put some data here. The first one that we want is an endpoint that'll give us the startup time. Okay, so string startup turn, what do we want to do? We want to say var delta equals duration dot between start and stop, right? Okay. And we're going to do dot get for these. All right, there's the delta. And we want to just return that as a value. So we say return delta dot to string. All right, there's the startup endpoint. And now we're going to get the dog data from the database just to demonstrate some basic database behavior. So record dog integer ID string name string, sorry, let's just do local date dob. Okay, it's just a dog record. I have a database table here for dog data. Okay, and dog repository extends list of CRUD repository dog integer ID. All right, so there's that. And let's just inject that repository here, dog repository. Add that to the constructor. We'll say this dog repository to find all. Okay, and we'll return dog. All right, that's pretty good. So now we have a way to get the data from the database to prove that that's working. We have an endpoint to give us a text, a representation of how long it took for the application to start. And then finally, we're going to have an endpoint, I think, to retrieve something from the file system or from the class path rather. And you might wonder what that is. Well, let's just create a text file here called hello. Okay, hello world. Okay, and we're just going to return that endpoint. So let's see, get hello return resource. Okay, I think you can just return hello directly. So here we go. And static final resource hello equals new class path hello. Okay, and return hello. I think that'll work. Let's go ahead and just try it out. You know, what could we lose? Let's just make sure we're all set up. Okay, localhost startup gives me PT08. So actually, I think I can get rid of the PT. Okay, restart. Okay, so it's 0.79 seconds. Is that exactly right? I don't know. It says 0.73 here, but it says 0.9 for the total Java process. So this is a little, the number I'm printing out is a little bit longer than the one that Spring Boot is reporting here, and it's a little bit less than the number that is being reported here. But whatever it is, it's going to stay consistent, okay? So bear in mind, it's a little bit slower than this, a little bit faster than that, okay? So 0.79, so almost 0.8, right? So this is 0.7 closer, and this is closer to 0.9, and the number I'm reporting is closer to 0.8. All right, what about hello? Okay, hello. That's returning the string, great, from the text file, fine. What about the data from the database? There's our dogs. Okay, good. So now we have a working application. We know it to work just fine. Of course, I'm running everything in the IDE. That'll probably be the last time I do that. But now we know we have at least a working baseline application. Okay, so now let's try it from the command line, right? Like I just said, let's do that. So we'll go here and we'll say maven skip tests clean package. All right, and we'll just do java -jar target service snapshot jar. Okay, if we go here, startup time, it's 1.1. Okay, so here's the baseline. All right, now this is the absolute slowest we hope to get anytime today. So timings, sure. What about if we run the baseline, but with the AOT mode enabled? Basically, we're compiling these more efficient versions of the program. You know, during compilation, there's this transpilation that's happening. You can see that generated here, but by default, Spring doesn't load these until you tell it to. So let's restart, and here we'll say -d spring.iot.enabled equals true. Run that, okay, and now this number goes down to 0.9, okay? So, you know, pretty good. Let's see, 0.9, baseline plus AOT, okay? And by the way, these so far are cross-platform, right? We like that. These all work on any platform whatsoever. So 0.9, let's, you know, maybe that's a different number. Maybe it's because we just had some benefit. Let's just try running it again. Let's see if it goes. So it's 0.977 before, refresh 0.96. So it's about that number, whatever that number is, it's around there, okay? So it's, you can see we shaved, what was the number again? 1.1, so round up 1.2, and then round up, this is 1 point, you know, it's just 1.0. So we saved about 200 milliseconds just by using the AOT version of the code. It's still Java, it's still using the JRE and so on, but I'd say we got some pretty good results here, okay? Not bad at all. Okay, so we've got our application already doing better just by changing a few things in the way that we compile and run the program. Can we do even better in a sort of generic cross-cutting, cross-platform kind of way? Well, yes, we can. We can use AppCDS. Now, this is a relatively new feature that was introduced in Java sometime in the last, I don't know, 5 years. I don't know when it was introduced. I'll need to look into that. But either way, it's fairly new. And we just debuted support in Spring Boot 3.3 for easily capturing class data sharing information into a file, and then you're using that to boost the performance of a subsequent run. This is a common idiom you'll see in most of the techniques today, which is that if you really want to optimize your program, you benefit from having a training run, during which time you can capture information about the behavior and the memory allocations and the performance of the application, and then use that to create a sort of pre-computed index that then gets fed into subsequent runs to better boost performance. So what we're going to do is we have our program. We're going to compile it as always. Now let's go ahead and run the program to extract out the contents of this Uber jar, which is about 30 megs, into a directory of the program code plus supporting classes. We'll use some of the tools in Spring Boot 3.3 here. So this is jar mode equals tools, but it's otherwise we're just pointing it to our Uber jar, and we're running the extract command which is available when we have jar mode equals tools. That has created a directory here called service, which has now a, let me see here, if we go to the directory, open in Finder, you can see that this in turn is about 25 megabytes look at this though. This is 24.6 megabytes, and this is 215 kilobytes, so about a fifth of a megabyte. All right. So we've got the directory, standalone directory. We don't have an Uber jar anymore. Now we want to run the program, the extracted jar, not the Uber jar, and use it to capture a class data sharing JSA file. And that file is the key to optimizing the performance of subsequent runs. And we're also going to run this on the AOT mode as well, right? We want AOT running as well. We're going to tell this to start the Spring application context, but to exit when we get to the on refresh state of the application. So the application context refresh. So it's going to run just as far as it needs to get all the beans sort of initialized and working, and then exit immediately, okay? And that allows CDS to do its work. So let's hit enter. All right, so you can see it ran. It printed out some warnings, which we can largely ignore, and then everything else is there, right? So it just did what it's going to do. If you go here now, there's application.jsa. Go back to our folder here, and you can see this is 36 megabytes. So almost 10 megabytes more than both of these combined, right? But it's kind of interesting. It's got a lot of information in this file. This file is key. Don't lose that. And then finally, we're going to run the regular jar, not the Uber jar, again. But this time, we're going to point it to the JSA file that we just computed and dumped out into that directory. And of course, we're going to do so in the AOT mode. All right. So we ran that. It started up in 0.3 seconds on my machine. Let's go to the browser here. And you can see it says 0.42 seconds, okay? So again, a little bit slower than what Spring Boot is printing out in the console, but incredibly, incredibly fast either way. So half a second, less than half a second here. But everything we've looked at so far has been completely cross-platform, part of the JDK itself. The next thing we're going to look at, of course, is our old friend GraalVM. Okay, so GraalVM is it's an open JDK distribution with some extra utilities. It gives you the most bang for the buck, I think, but it is not free. You will probably have to be aware of some of the limitations of the native image compiler, namely that it requires configuration whenever you try to do things like JNI, like reflection, like serialization, like JDK proxies, like resource loading, etc. So these things require configuration. A lot of times, Spring Boot will know what to do for you out of the box, right? It'll just do it as you expect it to, but it can't know everything, right? And so, for example, it's not going to know what to do with our resource file. It doesn't know that we want to include this in the native binary. So we have to go out of our way and tell it. So we'll create a hints class here, implements runtime hints registrar. Okay, add this, import runtime hints dot class. Okay, and in there I'm going to say hints.resources.register resource hello. Okay, that's all. Not a big deal, but I did have to do that, right? And if I had some bespoke reflection that I was doing inside of a method, for example, I might say hints.reflection.register type, for example. I mean, I can do all these sorts of things, but you just got to know that that thing is there. For a lot of the use cases, for just stuff you're doing with Spring, it should just work, right? Hopefully you'll never need to know about that stuff. Okay, so how do we make this stuff work? Well, let's get rid of the target directory. And here we'll do maven skip tests native compile, and we'll let that run. And this is my least favorite part. This will take a long time, and so we're just forced to let it finish. This is my least favorite part because I get really bored really easily, my friends. I get really bored really easily, and I don't like waiting for these native image compilations. It's quite distracting, and unfortunately, I'm in a situation now where I understand this famous and wonderful XKCD cartoon, xkcd.com 303, which posits that the #1 program excuse for legitimately slacking off is my code is compiling. You've got these two nincompoops goofing around while their boss yells at them, "Hey, get back to work," and they say, "Compiling." "Oh, carry on." I get this joke now. I don't want to get this joke, but here we are. It's 2024, turning out to be quite a weird year indeed. And I get really bored. I get bored enough, in fact, that I start to hear elevator music. You know that music you hear when you get in a lift and you're waiting for the lift to get to where you're going? It's interminable. It's meant to never have an end or a beginning, so you don't know exactly how long you've been trapped in the lift. And I start to hear that music that they play in my head when I do these long running compilations. And I thought, gosh, wouldn't it be great if everybody could hear that music. So I went to Oracle and I said, hey, Oracle, would you play elevator music during the native image compilation process, please? And I said, I already hear elevator music in my head while I do these sometimes long running compilations. I just like everybody else to hear it too. Thank you in advance, and I appreciate your amazing work. And I really do. I appreciate their work. I got some great responses, including this one from Red Hat's Andrew Din, a distinguished engineer, Red Hat Java team, OpenJDK project reviewer, a Byteman project lead, and a Graal developer. And he suggested, could you make it this elevator music, which is a soundtrack. It's some elevator music lifted from the soundtrack for the first Pierce Brosnan outing as James Bond in the 1990s, called GoldenEye. It's the video game for the movie, which came out in the 1990s. So it's a soundtrack for the video game for the movie from the 1990s. I think it's a great clip. I'm not going to play it. And then we get this suggestion, which says, I would add that using beeps in general, not only for native images, really helped me to reduce development time. That's true. I mean, that is true. My stupid microwave will make a ding sound. Why can't my multi-million line compiler do the same thing? Great idea. And then I get this response. And this is from Dr. Fabio Niephaus. He's a researcher on the GraalVM team at Oracle Labs, a PhD graduate, and obviously very, very important to me. And he says, thank you for your feature request, Josh. The problem with playing music during the compilation process is that it's just fixing the symptoms, and we've been and are still working on the cause, making GraalVM native images more efficient in terms of time, memory, and CPU consumption. Okay, go on. He says, I have prototyped a -- Josh Long mode, and what that would do is it would load, you would run the compiler like so. You would say native image, you'd say native image -- Josh Long mode, and you'd hear music. Don't let the fact that this is an image stop you from understanding that there's music playing at this point. And then it would say music brought to you by Josh Long. Very, very good. And then of course you're still wondering, now you know why it's here, but you're still kind of bored. You want something to look at. And so it'll print this out. So I'm hoping this gets merged into the native image compiler sometime soon. Here's hoping. Anyway, what were we doing? The compilation. Right. Okay, so that actually finished like a fair bit ago, like 3 minutes ago. That is embarrassing. Okay, so target, and you can see here, if I go to the target directory, -hs service, the native image is 87 megabytes, okay? And it's not a jar. This is a Mac OS specific binary. I can only run it on Mac. If I wanted to run this on Linux, then I have to compile on Linux and then ship that in a container. Or if I did the compilation in a Docker image, such as what build packs does, or in the build step for a Docker image, then I could, I would automatically get a Linux container anyway. So I could build that on my Mac and then ship that to production. So here we go. Start that up. And it is, how did we do for the startup time on this one? Localhost startup time, 0.1. So clearly much, much better than everything else so far, but with the compromise that you have to take great care when loading things dynamically and doing anything that might violate the sanctity, the hermetic seal of the type system. But this is, almost 12 times faster than the baseline. It's almost a tenth, an order of magnitude faster than just using the regular AOT in the baseline. It's almost 8 times faster than using CDS. So it's a really good result. It also has the benefit of taking much less RAM. This takes about an order of magnitude less RAM. I haven't even bothered checking the RAM for all the other ones, since that's really not the win that you're looking for when you use those technologies. But here's the RAM for this one, measured in kilobytes. So you divide by 1,000, that's 111 megabytes of RAM. Now, go to like CNN.com in Google Chrome, look up the sports page, and you can get it to go to 500, 700, 1,000 megabytes of RAM. Just one tab in one browser can do that. So the idea that we can have a scalable, virtual threads aware, a sort of native image like this and have it start in just 100 megs is a wonderful, wonderful result. And of course, this requires less from the JDK, and therefore that requires less from the operating system. So you could actually use a smaller operating system distribution for native images as well. Big fan of GraalVM native images. But can we go faster? And yeah, it turns out there's actually another thing we can do to go faster still. So let's return to our build, and let me get rid of the CDS stuff, get rid of that. Okay, what can we do now to go even faster still? Well, we can use Project CRaC. Project CRaC is coordinated restore at checkpoint. Based on a Linux technology called CRYU, it's a way to, it's based on a Linux technology called CRYU. It allows you to capture the runtime memory of the application and then write it out to disk and then use that to restart the process. And it's not like CDS captures just the Java classes and things related to that, but this captures everything about the process. And that can be a little bit of a problem because you might have things in the memory of the application that you don't want written out to, a file system unencrypted, right? For example, database connection passwords or logged in users or whatever, right? And so it works pretty well. It's a generic approach to optimizing applications. It only works on Linux, and it requires you to be a little aware of this life cycle, right? So the basic idea is you run the process, you take a photograph of the contents of the process's memory, and you write that out to disk. And right before that photograph happens, before that checkpoint happens, you want to make sure that you have a chance to clean up all sort of ephemeral network sockets and all database connections and secrets and all that stuff. So there is actually a mapping here in Spring to the Smart Lifecycle interface, so you get a chance to clean up your state right before the application gets changed. So let's go ahead and do that here. And I'll bring in this CRaC dependency onto the class path, and we can create a simple example, a very simple example, sort of a CRaC component, just as an example here. And okay, we're going to create a component here. And let's see here, private final atomic boolean started, or actually I want to say running, right? New atomic boolean is false. And we'll say this implements smart lifecycle, and we want to implement those methods. So smart lifecycle stop implements smart lifecycle, and we want to implement these three methods. Okay, so we're going to, so let's create a component that implements this lifecycle. Okay, so we'll say smart lifecycle, or sorry, CRaC component implements smart lifecycle. We'll just implement these three methods here, make this a Spring component, and we'll have private final atomic boolean running. Okay, and we'll say if this dot running dot compare and set false is true, then CRaC component started. All right, and we're going to do the opposite down here for the stop. We'll say if it's false and then true, stopped. Okay, good. And then we're going to return the state here via the running boolean. Okay, so there's a very simple test. This is going to get, this start method will get invoked after we've started the application from a checkpoint. This will get invoked right before we capture the memory of the contents of the process and write it to disk. So this is a good chance for you to null out any passwords, to disconnect or close any database connections or network sockets or anything you don't want being written to the disk because it's junk or sensitive. Okay, so this is your after restore, and this is your before checkpoint life cycle. These are also just regular Spring life cycles. So when you shut down your application, Spring Boot will automatically call this method. And when you start up the application, it'll call this method. So it's just a good thing to have to manage the life cycle of your components in general. So we've done this. We've got this here. We've added the CRaC dependency to the build. Now we need a Docker file, because remember, this only works on Linux, and I very clearly am running on a Mac. So I'll create a Docker file here. All right, here's my Docker file. I'm using Ubuntu from the April 2024 distribution of Ubuntu. I'm using Java 21 on Zulu, which is the Azul Systems implementation of OpenJDK. It's their distribution of the JDK. It includes a bunch of other stuff proprietary to them, but it is a Java compatible version. It includes a few extra things, including this Project CRaC. Note that OpenJDK, the core distribution from the OpenJDK project, and most other distributions don't support Project CRaC. So this is one of those things where only a few vendors support it. Liberica supports Project CRaC, and it supports GraalVM. So it has forks or implementations of both of those technologies in the same JDK. But and you can use that. I could have used that for my GraalVM demo as well. One distribution to get GraalVM and CRaC and CDS in the same JRE, in the same JDK. So this is the Azul Zulu Java 21 implementation, right, for Linux using ARM, not x86. You could use x86. There is an x86 distribution, but I'm using obviously an ARM CPU. I'm using Apple Silicon, and I'm going to tell it to download this file and then put it here in the Java home directory openjdk.tar.gz. The Java home is opt.jdk. So there's that. And then when it's going to, in the build step, again, it's going to extract the newly downloaded zip file to this directory. It's going to strip the components and then delete the original tar.gz. It's going to make this directory called opt.crack files, where we're going to store the computed checkpoint. And then we're going to copy the built artifact from our local macOS host directory, the target directory, to the container opt app service 001 snapshot jar. And we're going to publish this port. Okay, so let's now build a Docker image after we've built the image. So rmrf target, okay, we'll do maven skip tests clean package. All right, now we need to build the Docker image. Docker build dot -t crack. I'm going to call our container crack. It's going to download the Docker image for Ubuntu, and it'll download this JDK, which happens pretty quickly on my machine. And we run that, and we built out a local container called crack. Now I can use this. So let's run this. Docker run privileged -it -e. Here, friends, since we're running in a Docker image and we need that Docker image to connect to our macOS host, I'm going to say host.docker.internal, and get that way it can route to our SQL database running on localhost on my Mac. Okay, so -rm -p to publish the ports 8080 to 8080, give it the name crack, and then run the Docker image called crack. Okay, oh, it's already being used. Do we already have the port somewhere? Oh, we do. Okay, let's control C the downloads. Good. So that's fine. Control C this again, and cd docker ps docker rmf. Okay, take 3. Let's run this again. All right, there it is. And we're now logged into this running container, and now we can, inside the shell, we can see what we've got here. Opt crack files is empty. Opt app, there's a jar. Now we're inside the shell. Now we're inside the shell, and we're inside the Docker image. Let's run the program. Okay, -xx crack checkpoint 2 equals opt crack files. And friends, the capitalization of these attributes is incredibly sensitive, so just be aware of that. Opt app service. Okay, run this. So there you go. The Java process is up and running in the Docker image on Linux. Okay, so I'm not running on my Mac anymore. It thinks it's running from opt app blah blah blah. We're gonna go to another shell on my Mac, and now we're gonna log into that. So we're gonna say docker exec itu root crack bin bash. So we're logging into the same shell, and then we're gonna capture the checkpoint, and we're gonna need to know the process identifier. So 12 is that, and we'll say jcmd 12 jdk checkpoint for this. Run that, and you can see it captured a checkpoint. And over here, you can see that it exited of its own volition. By the way, you can see crack component started and so on, and then stopped. So the regular life cycle kicked in because it's just a regular Spring Bean. Okay, so now we have, or at least we should, opt app. We have this, and then crack files. We have all that stuff. Okay, that wasn't there before. Now we can restart the application in the first shell here using that checkpoint data. So Java xx opt crack files. Okay, and that's it. We're not going to do anything else. We're just going to restart from that data. And you can see that now crack component started. We got a chance to reinitialize based on that life cycle, but you don't see the rest of the program, right? You don't have to worry about all that stuff there. And so here it is, 50 milliseconds. Now, if we go to the startup page, it still thinks it's 1.2 seconds, right? But it's not. It didn't recompute anything. It's exactly at the same point in the process as it was when we took the checkpoint. So this is the startup time, basically, that we saw when we took the checkpoint. It's not the recomputed value. Isn't that amazing? Like, so it's really fast in that it's skipping all the computation. You're just going straight from like nothing to memory in RAM. That is a running process. The result is obviously a really good result. So you can now take those crack files and all that, and then containerize that, and then run it on any architecture, and it'll skip all that computation, all that stuff that it took to get warmed up, all that other stuff will just get redone for you. What about the database here? Well, go to the dogs database endpoint, and it still works as well. So it reconnected the data source, even though obviously you don't want that being written to the memory. So it's not writing it to the memory, it's recomputing that, but it's working just fine. Friends, This has been a very quick whirlwind tour of a number of different strategies that you can use to make your application fast. First, we established that Java is already pretty darn impressive. Really, it really is impressive. Then we looked at things like virtual threads, which give you less RAM and it can help your ability to handle more requests, and it's free. So spring.threads.virtual.enabled equals true. Then we looked at using AOT transpiled code just on the JRE with spring.aot.enabled equals true as a -d argument when you run the Java program. And then we also configure the Maven plugin to use and process AOT Java code. And then we looked at CDS, which is a new technology in Spring Boot 3.3. We looked at GraalVM, which is something about which I'm sure you've no doubt heard me speak before. And we looked at Project CRaC, about which I've spoken before as well. And all of these things improved the startup time considerably. The first three things we looked at all work cross-platform. CDS, of course, is one of those things that works cross-platform. We looked at GraalVM, which of course is cross-platform, but it requires a lot of other concessions, and it's only cross-platform insofar as you can compile and then run the binary on multiple platforms. You can't take the same binary and run it on multiple platforms. And then we looked at finally Project CRaC, which gives us the absolute best startup time from no process to a fully configured, ready to run process in, what was that number again? 50 milliseconds, right? Everything else we've looked at, including GraalVM, is 0.1 or more, right? So this is 50 milliseconds. So CRaC, let's say it's not, so it's 50, it's 0 point, is that right? 050, there you go, that's the right way. So this is 100 milliseconds, this is 50 milliseconds, that's almost 800 milliseconds. This is almost a 1 second, that's almost 1.2 seconds. So, and obviously this number is not exactly right because we didn't use the same methodology for capturing the start and the stop time. But either way, if we did, you could see that the results would be really impressive. My friends, I hope you got something out of this. Thanks so much for watching. I hope you feel empowered to take your applications further, faster with Spring Boot, and hopefully you can see why you need to be upgrading to Spring Boot 3.3 and Java 21 or later right now, not tomorrow, today. Do it now.